Today I'm going to be presenting on an introduction to the stochastic calculus. So just a brief overview of the topics. Why is it useful? A basic introduction to probability theory, random walks and Brownian motion, quadratic variation and why we need it, the uses in portfolio management and applications with stochastic calculus, using geometric Brownian motion, and a conclusion. So why is it useful? Every day, hundreds of billions of dollars go through the stock markets globally. And I think this figure is around 400 billion, every day over the last week. They fluctuate unpredictably every second. So they behave like a random system, not like a deterministic system, which is what most of us are used to, which regular calculus can't describe. So for example, if we have the curve y equals x squared, that's a deterministic system. If we know the value of x, we know the value of y. For example, if we had 2, we know the value of y is 4, and that's definitive. There's no randomness or anything. So here's an example of the stock price of NVIDIA over the last 2 years. We can see that it's quite random, it's fluctuating a lot. But what we can see as well is that there's still a steady increase across a big time period. And that's called the expected return, which we're going to touch on later. However, with stock prices, the price at any point is obviously random, but the key part is that it's independent of the past prices. So from all the way to 2023 to 2024, this part doesn't matter for what the future is going to be. Only the current point matters. That's the only point where the future is going to change, basically. I think I'll explain it. Okay. Probability is a way of assigning weights to possible outcomes. For example, if you flip a coin, the probability of you getting heads is a half, and likewise for tails. A random variable, this is a definition kind of, is a function that gives a value depending on the outcome of a random experiment. So with our coin toss, we can say that heads has a value of +1 and tails has a value of -1. We can call that random variable x. So x can take the input h or t, or heads or tails. So we have a 50% chance of getting a +1 and a 50% chance of getting a -1. So I expect that I'm going to get a half times 1 plus a half times -1, which is 0. But obviously, if it takes a value of +1 or -1, I can't actually get 0, right? So this is more of an average over all possible outcomes. So if I keep flipping my coin, I expect that I'm going to still stay around 0 and not say got to 100. This is called the expected value, which we denote with e of x, random variable, which is 0. And yeah, the definition is a weighted average over all possible outcomes of a random variable. Or we can think of it as just an average for our purposes. So random walks. If we instead of having one random variable, we have a sequence of random variables, x1, x2, x3, up to xn. But they all have the same sort of purpose, right? They will assign a value of +1 or -1, depending on the coin toss. Then we can define a new random variable, Sn, being the sum from x1 plus x2 plus x3 up until n, which we can write as that, which represents the position after n coin tosses. So for example, in this graph is an example of it. After 20 steps, we're roughly about 4, so +4. So that's, yeah. S0 is equal to 0, so we're starting at the origin, basically. So the key part is that the expected value of Sn is still 0. As on the last slide, we discussed that the expected value of x is 0. If they're all of the xn are expected value of 0, then Sn is also expected value of 0. However, this doesn't always result in a value of 0. As you can see, it fluctuates a lot, even goes up to 8 at some points, and it could be even more extreme in other cases. This is where the variance is used, which is a measure of how spread out the random variable is from the average. So our average is 0. So let's say we do three coin tosses. Sn can either be up to +3 or -3, that's the range of values. So our variance is 3, which is our maximum distance from the average. So variance of Sn is equal to n for our particular case. Okay, Brownian motion. If instead we flip a coin every small time interval delta t, say we flip a coin every 0.001 seconds, which is quite impractical, but we can still think of it as a 50-50 chance of going +1 plus root delta t or minus root delta t. So if we take the limit as delta t approaches 0, as it gets really small, then the number of steps per second approaches 1 over delta t, as delta t is less than 0, so every second we have 1 over delta t number of steps, right? So this approaches an infinite number of steps per second, as we're approaching 1 over 0, or 1 over a really small number. So this then converges to Brownian motion, which is a continuous random process, which means it's defined at every point. So for, say, 0.052, it's defined. And yeah. These are the key facts. So the expected value of W of t is 0, like we had for Sn and x. And the variance of W of t is t. So it increases linearly. Yeah. There's a couple examples of Brownian motion past. You can see it starting to look kind of like a stock price, random fluctuations. Although it's not shown on this graph, but Brownian motion can go into the negatives. So we have to do something to fix that, which is not right. So quadratic variation. Brownian motion is continuous, but it's too rough for us to take a derivative. It fluctuates way too much between any 2 points. So we need quadratic variation to measure it. And we do this because we want to, taking a derivative helps us understand something about the nature of a curve, right? So y equals x squared, you take the derivative, you get 2x. You know that the gradient increases linearly, and you can sort of predict what's going to happen in the future. We can't do that with this, but we can use quadratic variation. So let's say we take a time interval, 0 to t. So we can take any real number between 0 and t. For example, if we had 0 to 1, we can split up to 0, 0.1, 0.2, etc. And we call these values t0, t1, t2, up until tn. So if we square the increments, so we take each wtj plus 1, minus it from the previous wtj, and square that, which you can write as dw all squared, and the sum of that. For example, you could have wt of 1 minus wt of 0, square that, add it to wt of 2, take away wt of 1, and square that. And you keep doing that. And as all these increments, tj plus 1 minus tj, so t1 minus t0, t2 minus t1, as that goes to 0, this sum converges to t. So the quadratic variation is linear with respect to time. This is a very small time increment, 0.002 seconds, and you can still see it's fluctuating a lot. And that's just if I choose delta t as being 1 over 10,000, I think. But even with that fluctuation, we can see that this is the quadratic variation on the left, and then on the right, on the x-axis, we have time. So we can see that increases linearly, like t, like w, the sum equals t. So over a time interval of length t, Brownian motion accumulates t units of quadratic variation, which we can think of as accumulated randomness. So it's getting more random with time. So portfolios. Say, for example, I have a total wealth or portfolio value of x0 at time 0. In stocks and the money market, stocks, I'm sure you all know, but the money market is, for our purposes, is just a bank account. You can borrow money from it, you can lend money at a fixed interest rate. And delta 0 is the number of shares of the stock that we own. And S0 is the price of the stock at time 0. All this is at time 0 for now. So then our total wealth minus the cost of all the stocks that we hold, the shares of the stock that we hold, is invested into the money market. So your total wealth at time 1 x1 is the amount of shares you hold times the price of the stock at that time, plus 1 plus the interest rate. So say the interest rate was 5%, R would be 0.05. 1 plus R times the amount you've invested into the money market. And that's your wealth portfolio. Yeah. So if we rearrange this top formula, we get x1 minus x0, which is your payoff or your profit or loss between time 1 and time 0, is equal to the number of shares of the stock you hold times the difference in the stock price, S1 minus S0, plus the interest rate times the amount of money you have in the money market, basically. So instead of that, if we take a small time difference delta t, such that the stock price is changed by S of t plus delta t minus S of t, so like a really small time, between a small amount of time, how much the stock price changes, which we call ds. And the overall portfolio difference, or profit or loss, so our payoff after delta t, so we do x of t plus delta t minus x of t, and we label that dx. Yes. So then we get, basically substituting back into this, we get dx equals delta t ds plus r x of t minus delta t st times dt. The extra dt term that appears is just because the interest rate is, we're assuming the interest rate is continuous, so you continually every 0.001 seconds maybe you get a small amount of interest rate. And that dt adjusts that value for the small time period that we're doing it, because we're doing it in small time difference, delta t. So now instead, if we want to find the profit or loss or the payoff between any two different points, with the stock price and interest rate being continuous, then, this is the same formula as before, then we can integrate both sides of this equation. So the first one, we have integral from t to 0 of dx. We can think of this as adding all the small increments dx. So we would have, say, x of 1 minus x of 0. That's dx. Put that in brackets. You add that to x of 2 minus x of 1. And you keep doing that until you get to x of t minus x of t minus 1. Now, all of these x1, x2 cancel out, and you're just left with x of t minus x of 0. So we can think of the integral as a sort of continuous sum of dx. So on the left-hand side, we just have x of t minus x of 0. I'm not going to do the same thing for the other ones because it's going to get a bit complicated, but we can integrate r x of t minus delta t st dt with regular calculus, because we're doing it with respect to time, which we know how to do. But we can't integrate delta t ds using regular calculus, because what does it mean to integrate with respect to the stock price? So to fix this, we can write the increment ds as ds equals mu s dt plus sigma s dw. I'm going to explain what these mean. So mu is the expected return over a time period, and it adjusts it for the small time period that we're dealing with, dt. That's what the dt term does. And we talked about this at the beginning with NVIDIA stock price, right? We can sort of calculate it using past data. And that's, in our purposes, this is just a constant. But there are some cases where mu could be a variable, and it could be changing expected return, basically. Sigma is the constant of volatility, which changes based on what the stock is. For example, Apple might be less volatile than NVIDIA, for example. So it doesn't change as much every year or any time period you want to take. So dw is a small increment of Brownian motion, and this adjusts for the randomness. So this first term is your expected return. This is what you do based on past data. And this second term is the randomness. It accounts for the randomness of stock prices due to many factors. This is an example of geometric Brownian motion. That's this whole expression. Okay, finally, stochastic calculus. Replacing ds with mu s dt plus sigma s dw, we get this integral, this sum of integrals, and that represents our portfolio difference between t and 0. This first term is, as before, the price of our stock, the expected price rise of our stock between t and 0. The second one is your interest rate. So how much interest rate do you what's the cost of the interest rate from borrowing or lending from the bank? And the third one is the randomness, which is the one which we can't do with regular calculus, which we need stochastic calculus techniques. It's important that the expected value of this last integral is 0. So as before, it doesn't contribute anything to the expected value of our portfolio difference. This is due to the quadratic variation of Brownian motion. So it causes random fluctuation in the portfolio value, but it doesn't actually add anything to what we expect to get out of our portfolio. If we know the past data for a stock, for example, in a video, and if we have, the key part is we have a model for S of t, that part I'm not going to cover, but if we know how a stock changes in a way, we can calculate sigma and mu, which are constant of volatility and our constant of expected return. So we can find a value for x of t minus x of 0 using regular and stochastic calculus techniques, which is the key part. So stochastic calculus is a framework of modeling systems that are uncertain and random. For example, managing asset prices, portfolios, and financial derivatives. This relies heavily on probability and measure theory and analysis from mathematics, which I haven't covered that much in this presentation. But it's a very core tool used in quantitative finance, investment banks, hedge funds, and asset management. But the key part is that it's all about quantifying risk, structuring uncertainty, and finding the best outcomes over many possible futures. It's not predicting the future. That's the definitions in the presentation aren't purely mathematical. I try to make them intuitive. Questions? Yeah.
Do you think the kind of modelling using stochastic calculus is going to change or evolve moving forwards, or do you think it's kind of at a place where it fulfills the task it's moving forward?
I think especially with AI, that stochastic calculus is going to be used more, but I think that's more about replacing people. But then again, you can't actually get AI to trade with the stock market, I think. I'm not sure about that, but yeah. Yeah, Nag? I don't think new techniques are being developed, but I think we're developing different models. So like for the stock price, there might be different models. It depends on what the share actually is. Sorry, what does heuristic mean? Yeah. Yes, kind of tried to say that at the end, but it's not like, it's obviously, it's an average over many possibilities, so it's not actually like predicting what's going to happen. You don't know if it's going to happen, but you can know whether it's likely or not. So you know whether to, like, say, invest in that shares of the stock or not. You know whether it's worth it to do that.